Okay, good afternoon, everyone. My name is Aswin Sankaranarayanan. I'm a faculty at Carnegie Mellon. So let me begin by thanking Jinning for inviting me to give this talk. The work that we do, at least in my group, largely revolves around trying to build new kinds of signal models. But we've been largely looking at it in terms of what we can do with those models in the context of image processing, specifically image restoration, and higher level vision tasks in terms of shape and illumination reasoning of photographs and videos. And after in the last, I would say, many half a decade or so, we've been in this particular community, we've been uh, wrestling with this idea of what's called deep learning and how to use data-driven models for solving many of the problems that we have at hand. And from a signal processing point of view, much of the work that we've been trying to do in my group is trying to try to understand how to take deep networks and try to make them interpretable, try to build signal models out of them, and then use them for various signal processing challenges, much like what happened with sparsity and wavelet transformations in the early 90s and so on. So today, I'm going to largely talk about some of the ideas, work that we've done in the space, and perhaps try to make a connection to how it relates to image compression. I also realized that I'm between myself and lunch, so I'll try to keep this short. Okay, so sort of the overwhelming question that we deal with, and one of the questions that many communities wrestle with is what is an image, or what is a video, or what is a light field, right? And answers to this question have profoundly changed technology in many different ways, right? And I don't have to sell this to all of you, right? Things like JPEG, MPEG, JPEG 2000, all of this came from answers to this question: how to better describe an image, how to generate image models and use these models for doing compression, but also other things, restoration, denoising, deblurring, Inpainting, things, super resolution, things of that form. And my group, in the last many years, we've been working on trying to build signal models for solving image processing and computer vision tasks. And so today I'll talk about some of the work we've done in deep models, deep generative models, for many of these problems. And towards the end, as I said, as I promised, I'll talk a little bit about how this could potentially fit in a compression pipeline. So let's think about some of the classic image processing problems: super resolution, say Inpainting, deblurring, denoising. All of these can be, under some assumptions, can be modeled into what are called linear inverse problems. I have an unknown image X. I took some measurements via a linear operator A, and I'm obviously interested in inverting this set of equations to figure out what my image was. Right. Now, in each of these problems, the linear operator is different, but common to all of them is the fact that it is linear. And therefore, if I knew something about my image in the sense of what class it belonged to, I could invert it. And with this basic idea, what's been happening in the deep learning community, at least in the context of image processing and computer vision, is that each of these problems have been solved using ideas from deep learning. So you could build what is called a super resolution network to solve a super resolution problem, where you take in as inputs low resolution images and you produce outputs high resolution image. Similarly, you could train a deep net to take a noisy image and produce a denoised image, right? And each of these, and it's not a stretch to say that deep learning has been tremendously successful in solving all of these problems. But nonetheless, each of these problems is solved in isolation. And the networks that you build for one problem has little to do with networks in the problem, except perhaps superficial similarity in terms of the architecture and the training strategies used. So this led us to ask the following question. Classic image processing techniques reuse signal models to solve many different problems. If you took simple models like sparsity of gradients, you could in principle use it to solve any linear inverse problem. Couldn't we apply the same idea to this mindset of deep learning, where you train one network, but use it to solve any of these inverse problems, right? So the idea that we wanted to solve was, how do you train one net to solve all of these? So what network would we be training, and how would you use this network for solving inverse problems? And the mindset that we came up with is that we want to somehow understand not how to solve each of these specific problems, but try to build a model for what images are, right? And if you could build a model for what images are, we could solve any linear inverse problem simply by recognizing that all we are trying to do is a linear set of equations gives us some constraints, like things lie on a hyperplane. We're somehow intersecting this with our model of what a signal is. And the ability, what deep learning really gives us is the ability to model very complex geometries that which natural images are naturally present. So we could easily do this, for example, if we had a projection operator to the space of images. So suppose instead of knowing what the images look like, I learned a projection operator to the space of images, then you could apply techniques like iterative reprojection, where you progressively try to satisfy two constraints. One constraint being that you lie on this hyperplane that comes from your measurements. That, again, depends on the problem you're trying to solve. But you could then you also have the space of images, and you could keep projecting between the two till you find some sort of an intersection between these two spaces. So the insight that we had was that we could, instead of trying to solve these problems, each of these problems individually, you could instead learn a projection operator to the space of images. And this one single operator, a projection operator space of images, can be repurposed for solving any linear inverse problem regularized by images by simply using iterative reprojection, a very simple classical technique from optimization. So what exactly is a projection operator? It's basically saying, given a set of natural images, let's call it script X, find me the point that's closest in that set, given an input point, say V. So find the point that's closest within that set. So how do we do this? The immediate problem that we have is we do not know what the space of natural images look like. We have samples from it, sure, but what does the space look like? So this gets us into this sort of chicken and egg problem where we need to learn the space that we're looking at in order to learn the projection operator. So the way we do this is we first take the samples of images that we have, typically a large collection of image or image patches, and we perturb them. And once we perturb them, we try to learn a addition boundary between what an image is and what's a perturbed image. And once we have addition boundary in terms of something that classifies between these two, we can now try to learn a projection operator that brings us back from one class onto the other, from the class of perturbed images to the class of natural images. Right? And we can play around with all sorts of different perturbations to create more and more complicated distractors. Once we have these, once you have an initial estimate of what this projection looked like, we could progressively refine the addition boundary so that we have a better sense of what we are trying to classify against, and therefore a better projector. So this basically is an algorithm that we call OneNet. It learns an image prior in the form of a projection network, and we've used it to solve many different kinds of image restoration problems using iterative reprojection as our backbone. So here are some results, right? So what you see on the left is the ground truth, in the middle, the measurements that we are taking. This is for an inpainting / demosaicing problem. And on the right, what you see is a reconstructed output from this technique. In the middle, you see by cubic interpolation, just to get a sense of what linear techniques do for the same kind of problems. Here's another comparison. This is on denoising. So here's a ground truth image, a noisy image that we generated from the ground truth, a classic pre-DeepNet denoising technique called BM3D that's based on patch consistency within the same image, and what you get with OneNet. Right? So you can see sharper textures, right? Lesser artifacts, especially in regions where there are edges and textures. Okay. So let me switch gears now and talk a little bit about a different body of work that we have done, and this one in the context of higher level reasoning that we did on images in terms of estimating shape, reflectance, and illumination in a scene. Right? So this is a classic problem in computer vision. Right? Given an object, let's say that helmet, what is it made up of? How does it interact with light? What is its shape? Right? How do you render new views of an object? And what you see here are the kind of results that our techniques produce. So on the top, the images that you see are the input images. These are typically collected of an object under different illumination. And what you see in the bottom, the rendered video, is estimates of shape But more than shape, we also produce estimates of the shine or the reflectance of different pixels on the object, right? So this particular helmet has a lot of rust on it, and different objects sort of bend light differently depending on how rusty they are. And we can capture all those details. We can model them, estimate them, and use them to render the object in the under new poses. Okay? So we wanted to say take the same mindset and and use learning-based side formulates on top. So let me describe a different problem. One where it's much easier to understand the link between all the different variables that come into play. So let's say that I have this photograph, and here this photograph is being illuminated by multiple light sources. A blue light streaming in from the right, and yellowish light streaming in from the top. And let's say for some reason, right, I wanted to separate this into two photographs, each being illuminated by exactly one light source. It's almost as though I switched the other light source off in the photograph. Now, the physics of this problem is as following. If I'm looking at the intensity at some pixel, the color, basically the three color intensity at some pixel, this is formed because there was a light source, which is described in terms of a spectrum that got illuminated at that point. The object itself had some geometry in terms of its shape and how it was oriented with respect to the light source. And the object also had a color. So this particular object was red, so it absorbed all the green and blue wavelengths. It only emitted back the red wavelength. And then your camera sees what it sees based on its own color response. And the net result is this your image formation equation. It's a product of the illumination in the scene, the shading, which is a function of the geometry, as well as the reflectance of object, which has to do with different objects absorbing and reflecting light of different spectrum differently. And you can make it more complicated by putting in angular dependence of shine and reflectance in a different sense on top. And we've known how to solve problems of this particular kind in many different ways in computer vision. What we wanted to do was a pipeline that could rely on that knowledge for a learning-based formulate. So let me give you one of the solutions that we came up with. So again, given an input image, we first train a network that produces what are called reflectance chromaticity, which is basically the color of the object itself, not of the light source in the scene. From this, we can get a sense of both the light source, color of the light source, as well as the shading in terms of how different pixels interact with different light sources. And from that, we could in turn obtain separated images of the following form. Right? And the key insights that we brought into this was a previous work where we had this exact same pipeline of reasoning about reflectance, shading, illumination colors, and finally separation, using a purely physics-based formulate where we tried to attack each one of these one by one. But using that as the guidance, we could now train a network that could perform the same thing. But more importantly, since all the intermediate variables, the reflectance chromaticity, the shading, and the separation are functions that we designed that we wanted to fit, we could in principle go in and tinker with these and change the reflectance of the scene and get a new scene, which is fully consistent with the lighting and shading, but only that the textures have been changed. So it basically makes our network, our solution, it allows us to change the solution to maybe to edit it in a certain way, to edit the scene in a specific way. Let me show you how this looks in practice. So here is an outdoor scene. There is this yellowish light coming from behind the camera, and then there's skylight, which is distinctively blue on top, right? So let me show you then the separated images that we get out of this network. So here is one of them. So here we switched off all the indoor lights, right? So all you're seeing is the image under just the skylight. And here is the image that you get with purely the indoor light with skylight switched off. It's almost as though the sunset, right? And you can also see, if you look at the building, these buildings out here, you can see that the lights actually switch off in the skylight, and they switch on when we look at the sun. So this kind of guidance that we give to deep learning, the models that we train, actually produces dramatic improvements over just a vanilla trained model that just tries to separate it without all this intermediate guidance. Now, the last topic I want to talk about is something that is that shares a lot of commonality, especially when it comes to the underlying mathematics with learning-based formulates. So let me describe it, and hopefully these commonalities will become clear. Let's say that I had a shape, right? Some object in the scene. I took a photograph. I got an image. And let's say I produce some estimate of what I think this object is. Okay. Now, given that I can simulate what the camera does in a real world, I could simulate a measurement or my image out of this estimate of shape. So here the bunny, and I get a predicted bunny. And I could compute a difference between these two things. I could compute an error between my measurement and what I predict based on this thing. And nothing is new out here. This is how we standard, we solve most inverse problems. We make a prediction, we look at the error, we try to compute a gradient based on this error and try to update our understanding of the world. But now, because I have a renderer, I can do a physics-based, I can approximate the real world physics accurately, provided this renderer is differentiable, right? So as long as my physics is differentiable, then the same mathematics that underlying deep learning can be plugged into any framework that involves learning. And I can use it to update the underlying sort of, in this case, the shape of the object. So we use this particular idea as well. So here in the context of estimating shape for looking around the corner. So it's something like, let's say something is happening behind that screen. How do I estimate it standing here? And again, these ideas of physics-based inverse rendering becomes extremely useful for obtaining highly accurate estimates of things, of objects in the scene. Okay. So for the last part, I'm going to take some time and try to put together a vision of how all of these could fit into a compression pipeline, right? Now, to be honest, I thought I would have to, I had my work cut out to me to convince all of you that this is potentially related. But after Maggie's talk, I think this is much easier because thanks to her use of, scene understanding and semantic segmentation, just think of this as one level higher in terms of object detection, shape, reflectance, modeling thrown on top. Okay, so the ideas, sort of the three ideas that I mentioned together is first that if the deep networks should be, or deep learning should be can be thought of as building a model for images, and which you can use for solving restoration problems, and therefore in principle for compression. The second was to use physics-based modeling for interpretable learning. And of course, the last one was using differentiable rendering to sort of have a physically realistic rendering pipeline within any optimization or within any particular model, be it analytical, like what we used to do in the past, or data-driven, as what we're doing currently. So at some conceptual stage, you could think of everything that you're doing as some sort of an encoder followed by a decoder with the latent space that you'd like to keep minimal in terms of its representation, in terms of its size, right? You could throw in on top ideas of scene layout, semantics, illumination primitives, and shape primitives. And to have a physically aware decoder, you would decode these, much like what we did in our prior work, in terms of first pulling out scene layout, and then shape, reflectance, and finally illumination. So that what sits under your decoder is a differentiable renderer that predicts what the scene looks like, or a piece of the scene, maybe an object in the scene looks like, and then you predict the residue based on top. I will stop here and skip some slides and just leave you with sort of summary slide. And I'm happy to take any questions. Thank you. Okay.
What are the data that you use for the second part when you do the modeling for the shape?
Right. So a lot of this, a lot of this, actually the illumination modeling work relies on being able to know all those intermediate things and it's not easy to capture that kind of a data. So what we did for that particular work was we used some previous work that we had on a fully physics-based modeling to actually generate the training data. Okay. So what we did, we take images which have some level of illumination control, typically in the form of the flash on the camera being on. We send it through a pipeline that we fully understand, we trust under the modeling that we have that produces intermediate data, and then we train a network.
Yeah, and I think one of the reasons I ask is because I know I've seen for the example image you show, you have both sort of the lights that are in the scene versus there's also lights that are outside, which are kind of difficult to capture that information. Thank you.
Yeah, I want to go back to your first part here. On estimating the linear projector.
Yes.
I didn't catch. How do you do that? How do
You
you actually estimate that projector operator?
Oh, so we basically, given a perturb point, we search for the point in our we solve the optimization problem, which is minimize. There's an underlying optimization problem, right? We train a network that actually gives us that solution based on our knowledge of the. There are two networks that we are training. We are not just training the projection operator; we are also training the discriminator. Right? So what we are training is to find something that can pass the discriminator's test of whether it belongs to the image or not. So we don't actually do a point estimator in the sense that we don't actually say, look, this has to converge to this point into what you do in supervised training. But it's almost like an adversarial training where the output of this thing should pass the discriminator's test of whether it belongs inside or outside. Does that make sense?
So basically, it's a network that you train.
It's a network that I'm not sure if
I mean, like a deep network that takes the what do you call the observation and find the
and basically yes, and there's a discriminator which tells you whether it belongs to a class of images or not, and that basically enforces a check that this ends up being within the class of images. Right? And there is a penalty, which is that L2 penalty, that it should be close to your initial where you start off with, and that gets you the projection cost on top.
But that in itself is already doing, let's say, denoising or super resolution. So I don't understand why is that.
Oh, okay. So another way to think about this, I think you're making a good point, right? So another way to think about that first thing is if you train a denoiser, then in principle, you could use it to solve any inverse problem. That's a perfectly valid way of thinking about it. And in a sense, yes, we are training a denoiser to basically use as a projection operator. So I think that's intuitively that's exactly the idea, that any denoiser can be used to solve any linear inverse problem, and we are using one particular denoiser built in this particular way with some generative models thrown in, along with adversarial training to, I guess, get sharper images. Does it make sense? No.
No,
That part makes sense. I don't know then why do you need to, after that, have to do that iterative projection?
Oh, because your measurements, let's think of a different problem, say compressed sensing. I took some random projections of my data, right? So my measurement lives in it's not even an image, it's some data, right? So you can keep doing the sort of the adjoint operator that gives you something that looks like an image and projecting it, but there'll always be a measurement error and you need to use some iterative technique to solve that. I'm happy to, the math is fairly simple. I can sit down with you and work it out.
Last question.
Yeah, just.
No, it's
Okay.
you by default.
This one,
Yes.
then that one, then lunch.
Thank you for a very interesting talk. Did you, the optimization you're employing for the projection, is that standard?
Very standard.
And
So we use a technique called ADMM, alternating directions method of multipliers. Very standard. I just dumbed it down to call it iterative reprojection, but yes.
And how specific is it to L2?
Not at all. You need to build something called a proximal operator. And as long as you can build a proximal operator, which boils down to what's called a projection operator here, it's very, very standard.
Because you may want to try L1 for all sorts of sparsity reasons.
You could. So a lot of this work started off in compressed sensing, where the proximal operator was for the L1 norm, which is soft thresholding and things like that, right? And replace the proximal operator with a projection operator, then you get these class of techniques. So absolutely related to those classes. In fact, they're all inspired from compressed sensing work.
Thank you.
Okay, I think we have a
So-
final question over there, do we?
So just a question about computational complexity, which is becoming more important with AV1 and AV2 and so on. In your particular example with the decomposition of the image into all its constituent lighting and albedo and whatnot. You design networks to more or less predict the output from traditional algorithms to generate those things, right?
Yes or no? In part, at times, yes. But
So-
go ahead, yeah.
What is the relative computational complexity of the networks compared to the traditional algorithms? What was your experience?
That's a great question. So, can these networks compete with, say, analytical models, right? So, sort of the pieces that I missed was the analytical models were not trained on, were not developed to run on the same kind of information. Like many of them were multi-image techniques that required a lot more images to do the same task. But under the setting, they are absolutely faster than sort of learning-based techniques, right? But it's an apples and oranges comparison. All the solution, the sort of the image decomposition is solely from a single image of the scene, while all the physics-based models require more than one image to solve it accurately or solve it correctly. So not a fair comparison, but in general, yes, you do pay. At least I've not done careful analysis of things like bit error rate and things of that form, or decoder complexity. And those are things that are definitely not considerations when we try to solve these problems, because we are trying to do in a completely different context.
Sure. Okay, thanks.
Thank you.
Okay, thank you.